Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 27th of June, 2025 T, 2 hours, 29 minutes, and 58 seconds, 0.0000. This paper, published just a few days ago, introduces a method that maintains over 98% of a model's performance, while cutting its computational cost by almost 70%. The paper is titled LLaVA-Scissor, Token Compression with Semantic Connected Components for Video LLMs. And it's a completely training-free approach, which is really interesting. It tackles the challenge of processing long videos, which can be very expensive, by finding and merging redundant visual information to make the process much more efficient. On Hugging Face, you'll find the 8 billion and half billion parameter baseline models, complete with code examples, to get you started on describing videos. Alright, so to see how this new method is different, the authors provide a great illustration. When a model processes a video, it breaks it down into small pieces, or tokens, each representing a bit of the image. The goal is to compress these tokens. Now, existing methods often miss key semantic regions, which are just areas with unique meaning, or they introduce redundancy by repeatedly keeping similar information. This new two-step spatio-temporal approach is more clever. First, it finds and merges similar tokens within each frame. Then, it looks across all frames to remove duplicates over time. The result is a clean, efficient set of tokens that captures everything important without repetition. Building on that, this figure shows the pipeline in detail. On the left, we see the core idea, called Semantic Connected Components, or SCC. This method, it takes all the visual tokens from an image, figures out which ones are semantically similar, and groups them into clusters. You can see these clusters represented by different colors. Each one is then averaged into a single representative token. On the right, we see the full two-step process in action. First, this Semantic Connected Components method is applied to each frame individually. Then, it's applied again across all the compressed frames to remove duplicates over time. The final, much smaller set of tokens is what goes to the LLM. Okay, so moving to the results. This table compares LLaVA-Scissor against other leading compression methods on video question answering benchmarks. The key thing to look at is the retention ratio. That's just the percentage of the original tokens that are kept after compression. At a 50% retention ratio, LLaVA-Scissor performs great, achieving 99.7% of the original performance. But where it really shines is under aggressive compression. At just 10% retention, it maintains over 97% performance, while other methods drop off much more sharply. This really shows its strength in preserving critical information. This table then details the computational savings. It compares LLaVA-Scissor to other methods based on flops, which stands for floating point operations, and it's just a measure of how much work the computer has to do. At a 35% retention ratio, LLaVA-Scissor keeps 99.3% of the original performance, while cutting the required computations down to just 32.4%. And it gets even more impressive. At just 5% retention, it still achieves 94.5% performance, using only about 5.5% of the original computations. This really drives home how efficient the method is. So to wrap things up, this work on LLaVA-Scissor presents a really effective training-free solution for video compression. The core idea is its Semantic Connected Components method, which, as we discussed, is just a smart way to find and group similar visual information to remove redundancy. By applying this first within each frame and then across time, it dramatically cuts the computation needed. The key takeaway is its ability to maintain high performance even under extreme compression, which is where other methods really struggle. That's all we have for today. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex, and I'll see you next time.